this presentation. I'd like to just announce to our viewers and followers that Landscapes Live is accepting applications to become a part of the team. So if you're interested in that, send us an email. You can find more information in the website as well. So yeah, don't hesitate. Come be a part of the team. And now, Danielle, I'm gonna pass it over to you. Thank you very much for agreeing to present, and take it away.
Thank you, Pedro. Good afternoon, everyone. And it is really a pleasure to be part of this series of presentations. So thank you very much for the invitation, and I want to explicitly congratulate the organizers of this. It was really very helpful to have this, especially during the pandemic, but I'm very happy that this is going on, because it's a very useful tool to have available online on the internet. It's difficult to have access to so well updated state-of-the-art presentations about our field. So I want to talk about the role of lakes and the outlets of these lakes in pacing the life of landscapes. And the reason why I want to talk about this is because it's very related to two well-known broad open questions that you are well familiar with. Can we quantitatively predict river transport and the interactions between tectonics and climate to shape the topography of sedimentary basins? Or in other words, can we make any quantitative prediction? Can we go back? Can we use our models to go back in time and extrapolate our sparse data? And another question is, what is the timing of transient topography? How, if there is anything like a steady state topography, when we depart from that, how long does it take to recover the some sort of equilibrium or steady state? And to this, I will make use of lakes and saddles. Why? Because lakes are ephemeral entities in geology, when they need a forming mechanism to form a topographic minimum, a basin, and when this mechanism stops, then lakes tend to fill with sediment and water until they either become overfilled and then they are eroded through the outlet, and then they get integrated in the tributary drainage basin. Or even if they don't get an outlet because there is too much evaporation and the basin becomes endorheic and closed, then they become a perfect sediment trap. And eventually, sooner or later, they will become overfilled with sediment. So as soon as this lake opens its drainage and becomes exorheic, then you're in a situation like Lake Victoria here, where the outlet digging deeper and therefore lowering the level of the lake, as you can see in these raised shorelines. All right, so I'm not going to talk about Lake Victoria, though. I will show other examples, both belonging to the long-term late Miocene to present drainage evolution in North Iberia and the Mediterranean. And then for outburst floods that may sound familiar, Lake Bonneville, Lake Agassiz, Lake Vitim in Siberia, and two landslides in the Yangtze River that caused outburst flooding. So let me start with some methodology, then I will go first to the long-term scenarios, long-term transient topography in Iberia. Then I will go to the outburst floods cases where outburst flood is produced by the overtopping of smaller lakes. And then I will show some new results about the Messinian Salinity Crisis using landscape evolution modeling. Okay, so let me introduce very briefly the numerical model that I will show most often in this presentation. It's called TISC. It's a planform pseudo 3D or planform 2D model. It has a cross-section version which is called tau. And as well as the name stands for, it incorporates simple approaches to tectonic deformation, flexural isostasy at lithospheric scales, surface transport, and basic climate, different climate approximations that can be used for the numerical runs. It's written in C. It's open source. You can access it in GitHub. It's not a parallel code, but the most computer costly run that you will see today, it takes about 1 week. So in general, it's something affordable, let's say, in terms of calculation time. Most often, runs take just a few hours. Okay, as I said, the model incorporates simple approaches to tectonic deformation. For instance, thrusting, preserving vertical shear, and this is used to calculate the distribution of load, isostatic load, that then we use to solve the flexural bending of the lithosphere equation and calculate the vertical motions in response to isostatic motions. As for the surface processes, I use a typical hybrid stream power law for fluvial transport. So it's first detachment limited. So it's a typical stream power. Just we need to transport the amount of the transported sediment with this reaction equation. So what we do is calculate the equilibrium capacity using transport capacity constant. And then we calculate the actual amount of vertical erosion or deposition as the proportional to the difference between the actual load, sediment load of the river and the one that it is capable of transporting in equilibrium. This we need so that because with just the detachment limited equation, of course, we would have only erosion and incision, but since we are dealing with lakes which are depositional systems, then we need to incorporate some approach to the onset of aggradation, sediment accumulation. Right. So of course, we discretize as usual the topography in a rectangular constant mesh. And we calculate the balance of water and sediment as usual in all landscape evolution models. We have incorporated underground flow, but I will not talk about that. And there is no facies or grain size tracking, but there is this group from University of Socorro who are presently working in implementing that in the code. Okay, let me show first example. Here, what you see, it's a planform view of an uplifting block between these two positions, and precipitation is calculated with an orographic model, orographic precipitation. So the wind is blowing from the left to the right, and as a consequence of that, you can see that precipitation is concentrated along this narrow band of maximum topography that develops on top of this topography. So, I'm showing this because I find really interesting and exciting that even when adding orographic precipitation to a topographic uplift, this adds a lot of complexity and feedbacks between precipitation and topography. And yet the system manages to, I'm repeating the video, the system manages to find a steady state topography, an equilibrium between the rates of erosion and the imposed rates of uplift. Uplift rate is constant all over this model. So you will see that erosion rates eventually get in pace with the uplifting rates imposed to the system. And then it will stop, uplift will stop at 20 million years. And then what you will see is just the erosion of the topography. So models do predict such steady state concept, even if they are difficult to detect in nature. But what happens in more realistic case scenarios for study, such as the Tibetan Plateau? We did some work here trying to couple the GPS observations, the motions in the very at the scale of the entire Tibetan Plateau, and trying to reproduce the development of topography and also this lateral scape of the crust as a result of the indentation of India against Asia. And in this model, note that the results are fixed. Position is fixed relative to India. So the indenter is fixed here, and what is moving southwards is Asia. Again, this is a planform view. Initially, you have a random topography. That's why you have so many lakes. Then what happens is that the indentation takes place, and the Tarim Basin, which is defined as a hard body in the middle of the Asian domain, is moving southwards against this indenter, eventually producing a topographic minimum here. And this topographic minimum, because of it's becoming larger and larger due to the ongoing indentation of the Indian continent, that is producing a topography below sea level that would be equivalent to the Tarim Basin today, and capturing all the drainage. You can see the rivers attracted towards that topographic minimum, and all the water being evaporated there. And the reason for that is that in this model, the wind is blowing from the south. So all the precipitation most of the precipitation is being captured in the southern flank of the of this so-called Himalayan mountains. And therefore, there is little precipitation, high evaporation in the north. And as a consequence of that, you have this drainage attractor, which is the Tarim Basin, because it's very low in the middle of high elevation. Our purpose here was to understand the propagation of deformation towards the external parts of the origin. I will not go into details of that, but I think what is relevant to this presentation is the fact that in more realistic settings like this one, every time that a river finds a better basin to drain to, like in this case the Tarim Basin, it will add a distortion in the drainage evolution of the entire system. So when you end up with these river profiles in the model, in order to interpret them, you not just have to look at what happened in terms of tectonic shortening or tectonic collision between the two continents, but you also have to think of what were the drainage changes that happened during that evolution. And that makes, of course, these systems very difficult to learn, to get something out of them, because of this superposition of tectonic, geodynamic, and surface transport processes. So that's why in the next I will show is a scenario. This is northern Iberia, in which everything that we can study there in terms of incision of the river network is post-tectonic. So this should make things simpler. These two basins, what is interesting about them is that they are like two twin systems in the sense that they have the same drainage area or nearly the same drainage area. They are both formed as a result of crustal shortening along the northern Pyrenean Cantabrian mountains in northern Iberia. So they are flexural basins initially. Both of them become endorheic before the Oligocene, and until this endorheism lasts until late Miocene. So there was a lake system there that is sampled in many areas all over these two basins, and both are filled with sediment after tectonism, and both reach a similar level of about 800 to 1,000 meters above sea level. And yet they, as you can see, they have a completely different topographic signal today. And what we want to understand is why. What controls this difference? Well, the difference can be better seen in this relief anomaly map. This is, you can see the basin to the left is the one called Duero. And the Duero has a very low relief at high elevation. This is what we use for this relief anomaly map. And this is in contrast with the Ebro depression, which is, even if they formed very similarly, and their sedimentary infill is very similar. Also, if you plot a section along the topography, you can see that very clearly. You can see that the roof or the colmatation of the basin is still relatively well preserved, whereas in the Ebro basin, everything is much more eroded, and the drainage network is deep incised, much deeper. This is the typical landscape that you see in the Ebro, with lacustrine limestones in many places, harder rocks than the surrounding siliciclastic sediments, and so the idea, the same pattern happens in many areas of the Ebro basin. So all these lacustrine and siliciclastic sediments are continental sediments are exposed with these patterns. So what we know is that at some point during the late Miocene, the basin became overfilled with sediment, and then the drainage opened, the precipitation of evaporites and lacustrine sediments stopped, and incision started. And as a result of this incision, we also know there is a higher amount of uplift, isostatic rebound or uplift in the center of the basin, that it reaches close to 1,000 meters in rebound. Okay, so then in order to compare the two basins before going to the modeling, what we did was a search for new terraces using this automatized way in this article, and by dating with the cosmogenic isotopes of beryllium and aluminium, we reached values of incision of this order, what you have here. So what is important is that close to the outlet of this basin, of the Duero basin, the one in the left side, let's see it here. This is the outlet. This is the Arribes. The Duero is mostly damp, but you can still see the deep gorge excavated by this outlet of this old lacustrine system. Indeed, erosion rates, we estimated, this is not in this article, it's an older one, but they are estimated between 2 and 3 meters per kilo year, which is it's far larger than anything we have obtained in the center of the basin. And the pattern that we see is that the more you get far away from the outlet of the basin, the lower the erosion rates that are observed. This is unlike the Ebro basin. In the Ebro basin to the right, what you see is more homogeneous rates of erosion. In fact, they might even increase towards the west during some periods, and then you also see an acceleration, a clear acceleration of the incision rates based on all these references. Reflecting this, there are also evidence of drainage captures, like this one, which looks to, it hasn't been dated. We didn't find a way to date this, but this, it seems really nearly historical capture, in the sense that the distance here between the capture point and the beheaded river is only a few hundred meters. So this is I forgot to say, this is a capture of the Ebro basin, capturing an older tributary of the Duero basin. The place is called Ontomin here. And this is intriguing because this seems to be in opposition to what you obtain if you do the calculation of the chi parameter. And in this chi map, or this chi profile, you can see that what you would expect is the Duero to be actively capturing or aggressing the Ebro basin. So the interpretation, based on these observations, what we wanted to understand is why do we have this different behavior in terms of captures and in terms of what the chi parameter suggests, the opposite sense of drainage expansion. And what we said is this initial setup, this is a perfectly symmetrical topography. The only difference between the left and the right sides, which aim at modeling the Ebro and the Duero basins, the only difference is the width of the barrier that separates the left basin from the ocean and the right basin from the ocean. Everything else is identical. And by comparing this, let me stop this in the beginning. You see that initially, this is after one time step. So here you have already the Ebro lake has been shrinked by almost 1/2 very quickly. But initially they were, both were identical. And what happens is that just because of this narrower topographic barrier separating the right basin from the sea, the Ebro lake disappears very fast. The entire basin becomes entrenched by the river network, whereas the Duero River remains for several more million years before it reaches the present stage. You see, so this model was we chose as the preferred model because it preserves the top surface of the sedimentary infill in the Duero basin, whereas there is a large rebound, isostatic rebound predicted for the Ebro. And another interesting pattern that you can see that satisfies the measures I showed before is the fact that the maximum incision rates are happening near the outlet of the Duero basin. Yeah. And then during parts of this evolution, you also keep having sedimentation even if at very low rates in the boundaries of this lake, which is also something that is observed in the field. So there are, yeah. So what is our interpretation of this? The interpretation is also based on the study of nick points along the drainage basins. Lucia Struth, which is the first author of this article, found two different systems of nick points migrating through time, as the model predicts. One corresponds to the main nick point of the outlet of the basin along this gorge that I showed in a picture before, and that main nick point is migrating very slow, whereas another that is the nick point that is cutting into bedrock, and this is granitic rock, so it's a very low erodibility. Whereas there is another set of nick points which appear to migrate much faster towards the higher reaches of these all these tributaries. So that would explain why in the divide. Let me see if I no. Why in the divide you are today. You can see captures of the Ebro basin towards the Duero, whereas in the large scale, what you see is the ebb today, the Duero basin capturing and propagating the big erosional wave, still starting to propagate near the original outlet of the basin. Okay, so. Even if what we have seen is suggests that the disappearance of these lake systems happens geologically fast, and that is much controlled by the geometry we impose to the lake, to the initial lake, how deep it is, for instance. Depending on that, it will be incised very quickly, and the water body will disappear very quickly. But we know that in some cases, actually, this happens in much more rapid timescales. And this, as you know, when water bodies overtop, in some circumstances they generate outburst floods due to the feedback between erosion along the outlet and water discharge. So in these two examples, and this is a very tricky problem if you are not familiar with it, because in some cases you get this result, like this moraine lake that has overtopped and triggered a very large and destructive flood downstream. So it caused severe damage, whereas the one in the right, which was caused not by a moraine, but this is a landslide blocking a river in Pakistan, it forced to do a lot of excavating work before the lake overtopped to avoid the danger of outburst flooding. And they evacuated lots of people from the valleys underneath, and eventually nothing happened. So when the lake overtopped, the incision caused by this lake was not enough to trigger the feedback and cause a large flooding. But this indeed happens. These are, for instance, boulders that are thought to have been dragged by the Lake Bonneville outburst flood in the state of Utah and Idaho. And by the size of these boulders, if you accept their roundness is caused by rolling by the flooding waters, then you can see that we are moving in the range of millions of cubic meters per second of water discharged. So the overtopping of Lake Bonneville is clearly one that is well known to have happened in very rapid timescales. This is another typical deposit of outburst floods. So this is called run-up. And in the Altai, just to show what run-up is, let me show very quickly this model. This is we were using a sandbox device that we built in 2016. We use this for outreach purposes. So in this Altai flood, what happens is that a lake outburst is sending water with high energy, and this water is capable of, because of the kinetic energy, is capable of climbing when topographic obstacle is found, and then it loses energy. That's the green, what the green colors are showing, and these deposits are what you were looking at in this picture. Here you can see. So if you go here, what you see is essentially gravel, fairly rounded gravel that has been deposited more than 100 meters above the present river level. So this is outburst floods, and to model them, we just have to couple what happens along the outlet. It's what I will show now. It's a 0D model focused on what happens at the outlet, at the very outlet, and then we calculate the hydrogram by calculating the feedback between erosion and lake level lowering. So the typical equations, it's a basal shear stress-based approach. What we are using, I also use critical flow along the outlet, and with this we can calculate hydrograms like this, just to give you a feeling what controls what in here. The erodibility parameter is the one that will determine if the peak discharge is very localized and rapid, if the outburst flood is very intense and short, or if it is longer and less and with a lower peak discharge. That's the main parameter. The other important parameter, of course, is lake area, but that is usually known. So this we can fix because we know from the field. Okay, so here you have again the Lake Bonneville flow. We know the peak discharge thanks to those boulders and many other observations that have been related to the discharge of water, and you can see that it reaches about 1 million. That's the estimation for the peak discharge of the Lake Bonneville. And in the right, you have an outburst flood that is 7 orders of magnitude smaller, and it's an experiment with a sand barrier that forms a lake behind, and therefore in this experiment it's possible to measure in real time the discharge, and we can model this. That's the continuous lines are the models, and both can be fit. And in order to fit one and the other, what you get is a value of erodibility of this amount for the Lake Bonneville, 10 to the minus 3, and 10 to plus 1 in the case of the sun experiment. And if you plot this for many scenarios, each of these would correspond to an outburst flood, then what you see is that there is some consistency between the lithology of each of these outburst floods and the erodibility that the model needs in order to fit the peak discharges. And what I will show is that these outburst floods in blue and in green, they are roughly consistent with the values of erodibility obtained from long-term landscape evolution models, such as the one in the Ebro basin that I showed before. And so let's go to different examples. Sorry, this is a first interesting example of outburst flood in China, the Twin Beach outburst, because here two very similar outburst floods happened due to two landslides on the same river, the Yangtze River, and the very same place. And due to the different elevation of the barrier of the landslide dam, and due to the direct measurements available for the peak discharge, we can test the model and check whether with the same erodibility we can actually reproduce the two peak discharges of the first and the second flood. This would be the measured hydrogram for the second flood. And actually the model performs really well. You can see the fit of the model here with the first peak discharge, and the second one is that was measured over time. So that we have the curve in blue. And the only difference between these two models is the observed elevation of the dam, which is also measurable in the field. So this is good news in the sense that it seems like this, even if the model is so simple as what I explained, it still captures the basic response to the different elevation of each of these two landslides. And for that, we need this value for erodibility. Okay, so this is what I take as the best value for erodibility. We will have to skip a couple of, because I'm a bit in delay. So let me go now to Lake Agassiz. Lake Agassiz, here the question was different, because here the question is which one of the different shorelines or different levels of the lake was responsible for the outburst flood along the Athabasca spillway in the south. So here what we did was the opposite approach. We were a bit brave, perhaps, in assuming that this correlation is good enough. So we used this to put a limit to what would be a reasonable value for erodibility. And based on that, we concluded, and I'm open to hear your criticism, we concluded that the lake level responsible for the Athabasca spillway outburst flood was not the middle, was not the Churchill level, but it was the largest lake, the Lake Agassiz. Because otherwise we would need a much lower, much higher erodibility to explain the initial and final level of the lake before and after the flooding. Okay, so I will go to quickly to present some results about the Messinian Salinity Crisis. Very quickly, we are talking in this case of the largest documented endorheic basin, and there is a consensus that of when did this happen. This is something that happened in the late Miocene between 5.97 million years ago, and the Miocene-Pliocene boundary, which is defined thanks to this event. And there is also consensus that there is about 1 million cubic kilometers of salt trapped at the bottom of the Mediterranean Sea today. So this is very well quantified. This represents about 6% of the dissolved salt in the ocean that were suddenly, geologically very fast, trapped in the Mediterranean. And another number to keep in mind is that about 15% of the continental surface became endorheic during that period, in the sense that it was not draining to the open ocean, but it was draining to internal lakes formed in the Mediterranean and the region known as Parathetis. Well, this is caused by tectonic blocking across the Gibraltar Strait. I will skip this. And this is some views of the halite, the salt. This is the best outcrop, probably this mine in Italy, where you can see annual varps layers of about 15 centimeters in thickness of annual accumulation of halite during that period. And another evidence is the erosion of happening during the drawdown. This is the Ebro Delta. So this is just off the Ebro basin that I showed you before in North Iberia. And what you see in the seismic stratigraphy in 3D in this image is an erosion surface that has a very subaerial exposed morphology. And this surface, this erosion surface, is buried under several hundreds of meters of later post-Messinian Salinity Crisis sediment, plioquaternary. You can even see meanders in the coherence the data of this 3D cube. And the Messinian Salinity Crisis has a big, well, I wanted to mention, but I'm a bit short in time, that this there is the proposal that the end of this period happened very abruptly in the form of an outburst flood, but I will not go into that. This is based on the very fast transition from evaporitic to post-evaporitic normal open marine sediments in the Mediterranean. But what I want to talk about is about the last stage of the Lago Mare, because during the last stage of the Lago Mare, we have an open question mark, which is why after this desiccation and accumulation of halite during this period here, this stratigraphic column represents the halite precipitation, and then during the Lago Mare, right before the Miocene-Pliocene boundary, you get these weird deposits of fresher water. It's a brackish deposits or fauna of Paratetian provenance, so it comes from Asia, and also at a very a level that is at least at times very close to the present ocean sea level. And this is very intriguing because if you end up with a normal sea level in the entire Mediterranean, this period of desiccation, then why would you have a flooding afterwards? And also, so we were dealing in this group of people in this project, European project, so Giant. We were dealing a lot with this problem. No, why do we end up the Messinian Salinity Crisis with high levels of water instead of the lower levels that happen that are represented by these erosion surfaces that is widespread? Okay, so what I will show is that this is probably very related to the presence of these saddles and sills underwater today. So you have saddles in the saddle in Gibraltar, which is the one that separates the entire domain from the rest of the ocean. But then you have also sills that separate the western from the eastern Mediterranean, or the Po basin from the eastern Mediterranean, or the Bosphorus Strait separating the Black Sea from the eastern Mediterranean, etc. And all these, they play a very important role in determining the timing of this evolution. What you are looking at here is a constant weather, constant precipitation rates through time, but with a precession cycle, so 21 kiloyear cyclicity in the precipitation rates. And as a consequence, as a result of that, what you see is all these lake systems moving up and down. Let me show it faster. Now it goes much faster, and these ups and downs are very much controlled by the erosion happening along all these sills. And that's why initially, if you look at this panel, initially you have all the lakes at very low levels, but as they propagate erosion upstream and they capture further lakes located at higher elevation, such as the Pannonian Basin, you see, look at this example in the Pannonian Basin, is quickly removed due to the erosion marked in red here, is removed and drained to the Caspian Sea and eventually to the Mediterranean Sea. So it seems like one answer to our problem as to why is the level of the Mediterranean increasing through time and also oscillating very widely is due to the competition between these two phenomena, the precession cycle, cyclicity in precipitation, and the gradual incision of the sills between separating all these basins. So I'm done with it. So I have a few take-home messages just to remember some ideas. Like lake outlets are topographic saddles key in determining large-scale changes in drainage and landscape evolution. They facilitate, importantly, the drainage changes because the lake can find different saddles that can be used as the new draining outlet. And then climate or tectonically cancelled lake outlets, such as in endorheic basins, they become perfect sediment and water traps. And these landlocked basins, when they overtop or when they are captured, they open geologically very fast. But the transient landscape can last still for tens of millions of years. But however, the overtopping of captures of lakes occur in the form of cataclysmic outburst flood, depending primarily on the size and the lithology of the outlet. And to conclude, yes, the idea that future landscape evolution models should benefit from incorporating the relevance of these topographic basins, these topographic minima in the landscape, and the mechanics of this outburst flooding should be incorporated in order to better understand also the long-term and the short-term rates of sediment transport. Thank you.
Okay, thank you very much, Daniel. This was a fantastic presentation. We have now opened the chat for questions. And while people are still working on their questions to ask you, I might just go ahead and ask you a question myself. In your numerical models of the Duero and Ebro basin, where you have the two lakes side by side, I was wondering, yeah, exactly that one. I was wondering about the start of the beginning where you start imposing the changes. So do you wait until you reach an equilibrium landscape where everything, erosion rates or deposition rates are the same everywhere? Or how do you force the system?
Well, this was meant to not include any, you mean this model, I guess?
Right.
This is meant to not include any tectonic. So here the only vertical motions that you have are related to flexural isostasy in response to the rebound of this due to the erosion. So what controls the higher uplift in the Ebro is the fact that there has been much more time to remove sediment from this basin, and therefore it rebounds by more than 700 meters, as you can see here in this curve. But so we do not reach any sort of steady state topography because there is nothing to compete with here. The flexural rebound is not enough to compete with incision. It's just a reaction.
You just build the topography up to an elevation that is similar to, I guess, the Duero, and then you leave the landscape to erode.
Exactly. Yeah. So we start by defining this initial topography, and then we just let it erode. And then in response to that, there is the isostatic rebound in response to the unloading of both sediment and water. So what you see here, I was very quick, sorry. So what you see here is the propagation of these incision rates that go very fast in the Ebro side, but they are much delayed in the Duero side because the endorheic period lasts much longer, and the only reason is that the fact that the barrier is wider, so the erosional wave needs more time to propagate from the Atlantic side into the Duero basin than from the Mediterranean side into the Ebro basin. This was just one of the parameters we were testing. In the article, we show the effect of other parameters such as elastic thickness, for instance.
Right, right.
Elastic thickness of the lithosphere.
And I'm assuming the rocks are similarly resistant on both topographic barriers, both in the Duero and the.
Yes, because the I mean the linking erodibility with lithology, and it's complicated, no? And that's why we put so much energy in other works. I showed some of them in trying to find some relation between the erodibilities of outburst floods and the lithologies, so that we could have some order of magnitude at least of what are the numbers that we should put in these two barriers. But specifically in this experiment, the erodibilities are the same. And I think with this setting, it doesn't, we show the effect of erodibility, but it's not so interesting because it's very obvious. If you make this harder, then it will take longer, and if you, etc. No, there is a question.
Yeah.
Two questions.
Thank you for giving that answer. All right, so we have a question from Laura. Thank you for the interesting talk. 2 questions. You said that you could not date the Homino River. Why? Have all the terraces been eroded, or are there no accumulation terraces in the valley? And then the second question is, you just use augmented reality for the sandbox or actual water?
Oh, yes. Sorry, I was extremely fast with everything. I had too many slides. So, but yeah, the answer to the first one is there is no terrace. It's so young that there is really nothing. Also, it's very loose soil. The area it was cultivated until recently, and you go there and you actually feel that the erosion is propagating in very historical timescales, let's say. But no, there is no river terrace. However, in the same volume, so it's by coincidence is in this volume that you have here in the image. In this, there is another paper by Regard et al., and they look more specifically into field constraints of this. So if you're interested, check it. And as for the second question, did you? Yeah, it's augmented reality. Sorry, it's the typical sandbox augmented reality setup, in which you generate the water by just putting some obstacle in the middle of the detector. So, and this makes virtual water flow on the landscape. Yeah. So it's just a modification. If you want to know, it's a modification of this. I forgot now his name. the one who first shared this the setup for this augmented reality sandbox. Actually, I learned that the first ones that were first doing this setup augmented reality sandbox were Czech people. They were students from Czechia. They didn't diffuse it too much, but apparently they were the original authors of most of the software involved in that. Yeah. So the only thing we did is a small modification in the code to highlight the areas that have low and high energy. So you have high energy in red. So when you have a deep water column with a steep slope, then you get red colors for high energy. And the green colors are for low energy. So what happens is when the water goes up, climbs up the slope, it loses energy, and that represents deposition.
Okay, that's really interesting. So we have another question that is by Romano, and he's asking whether are there any beryllium-10 derived denudation rates available within the Tau basin? Erodibility can,
basin?
which is I'm not really sure.
Basins,
maybe
the two basins, maybe.
Oh, maybe the two basins, yeah.
Oh, the two basins.
Yeah. Okay, yeah, the two basins. So
yeah,
erodibility can
easy.
be better constrained, yeah, using relationship between erosion versus KSM.
Yeah, sorry.
Yeah.
Erodibility can be better constrained by using relationship between erosion versus KSM as well. Thanks for the talk. There are beryllium-10 available. Yes. This is why I was going a bit fast on that as well. But this is what I summarized in here. So I can't remember which ones are based on beryllium, but I think a good part of them, especially in the Ebro River. And this one, for instance, too. This is in this worldwide data set of compilation. I saw it. So yeah, the answer is yes. Most of these they are, I believe. Also including our own studies. So in this article and these two articles, you can find beryllium dating in combination with aluminum.
Okay, still waiting for more questions here. I can ask another question in this case. So it was curious here. So and it was a little fast for me to grasp, and so forgive me if I make you repeat something. The question that I had was about this chi contrast that you have between the two basins, and so is it correct that in this case, if you look at chi, the Duero basin comes out as the aggressor? Is that the?
Exactly. Yeah. So you can see it in the map or both in the along the profiles. So what this, if you look at this without knowing the region, what the first thing you imagine is like, okay, the Duero is aggressing the Ebro. The left is aggressing the right, and it will. But then what you see in the field is the opposite, and this is what we link to the transient landscapes, the very transient situation of the Duero basin, not the Ebro, which has reached more sort of an equilibrium, but the Duero is still, as you can see, is very far, very departed from equilibrium. And it is here in this region where the original outlet of the lake is that the fastest incision rates happen, and they are still starting to propagate upstream into the rest of the basin. And that's why we end up with this interpretation of the two different sets of nick points. One set related to the main nick point in the gorge at the outlet, and then the other ones which are controlled by the softer layer of sediment covering the basin. So, and it goes faster just because the erodibility controlling that that propagation is much higher. So I forgot to say, for instance, in this model, one important parameter, of course, is that the erodibility of the barrier of the dam separating the basin from the ocean is 10 times harder than the sedimentary infill. Okay, this is completely arbitrary. It could be 100, could be easily 100 times. But it does reproduce these two different speeds of propagation of erosion towards the divides for the main nick point and for the smaller nick points affecting only the sedimentary cover. That's the main idea of the.
I'm curious to see a chi map of those models to see if they reproduce the field example there.
I'm not sure if I could find it, but I will search for it. Yeah, if you're interested, because yeah, it's true. That would be an easier comparison, not to. But I mean, but this main. This is pretty obvious. I mean, both in you can also already detect that in the topography in this cross section, no? How the river profile of the Duero in the final stage, it has a concave up profile in contrast with the
absolutely.
In contrast with the concave up profile of the Ebro.
Absolutely. Yeah, no, it's just very intriguing, and I think these are phenomenal results. Okay, I guess we're out of questions, and I could stay here entertaining you, Daniel, for as long as I'm curious about your work, and so, but I won't do that. So thank you once again for joining and giving this amazing presentation. The talk should be online very soon. And otherwise, just thank you everyone for coming.
Thank you, Pedro, and thank you, Aditi. It has been a pleasure.
Our pleasure.
Thank you, Daniel.
Bye.
Bye.
Bye.